We discussed the relation between differential and integral equations in the previous lecture. In this lecture, we will discuss some problems of converting a differential equation into integral equations and vice versa. Consider a problem of converting this initial value problem into corresponding integral equations. In the last lecture, we already discussed that the initial value problem, the second order initial value problem, can be converted into Volterra integral equations of second kind. Okay, so this is a second order initial value problem because we are given the initial conditions. So we can convert this differential equation or initial value problem into a Volterra integral equation. Okay, so here we have the given differential equation is y double dash plus lambda y equal to f of x. So we are integrating over the interval 0 to x or 0x. Okay, so we will get integral 0 to x y double dash of t dt. We were taking the auxiliary variable as t for convenience. We are replacing. Instead of zeta, we are taking t here. Okay, it's for convenience, no problem. So y double dash t plus into dt plus lambda into integral 0 to x y of t dt equal to integral 0 to x f of t dt. So we are integrating over the interval 0 to x. So we have the integral of this y double dash t with respect to t is y dash t, and applying these limits we will get y dash of x minus y dash of 0 plus lambda into integral 0 to x y of t dt equal to this. Okay. Now the initial conditions are y of 0 equal to 1 and y dash of 0 equal to 0. So we can replace this y dash of 0 by this 0. Right. So y dash of 0 plus lambda into integral 0 to x is equal to this. Okay. So integrating again over the interval 0 to x, we'll get integral 0 to x y dash of t dt plus lambda into integral 0 to x into integral 0 to x y of t dt dt plus which is equal to integral 0 to x 0 to x f of t dt dt. Now here we know this is derivative of integral of y dash of t is nothing but y, that is and applying this limit we will get y of x minus y of 0, right? So plus lambda into by applying this we already discussed the this formula. It's also called a replacement formula. Replacement formula. Okay. So by using this replacement formula, here we have only two integrals. So 1 by 2 minus 1 factorial is 1 by 1 factorial, and we have to here we have actually x minus t power n minus 1. So here we will have x minus t into y of t dt. So this integral is equal to a single integral 0 to x minus t y of t dt. Okay, which is equal to here also we have integral 0 to x minus t into f of t dt. Okay, clear. So now this is equal to, from this we already the initial condition is y of 0 equal to 1, that is given. So we replace that. So y of x minus 1 plus lambda into x will give this. Okay. So yeah, this is equal to this. Clear? Yeah. Now this is equal to y of x equal to 1 plus, taking this right hand side, we will get 1 plus lambda into yeah, 1 plus integral 0 to x minus t is here, so we have already, so integral 0 to x minus t f of t dt plus lambda into integral 0 to x, here is x minus t, so taking to right hand side we will get t minus x y of t dt. So now we obtained the required Volterra integral equations. Okay, so this is the required Volterra integral equation corresponding to the given initial value problem. Okay, so this was our initial value problem. So this initial value problem we converted into the Volterra integral equation of second kind. Now we can try to convert this integral equation into corresponding initial value problem. That is, we are going to convert this integral equation 2 into the corresponding initial value problem 1. Okay. So here we have the given integral equation is this: y of x is equal to 1 plus integral 0 to x minus t f of t dt plus lambda into integral 0 to x into t minus x y of t dt. So our aim is to find the corresponding initial value problem, which is, we know that it is 1. Okay, that is, this is our corresponding initial value problem. So we have to convert that integral equation into this initial value problem. Clear? So for that, first we can find from this, we can find the initial conditions. So here this initial condition will be y of 0 and y dash of 0. So when we replace x equals 0 here, we'll get the initial condition at x equals 0. That is y of 0 equal to, from this, y of 0 equal to 1 plus integral 0 to 0, which is 0, and here also integral 0 to 0. So the integral will be 0. So we have y of 0 equal to 1. Yeah, here is 1. Y of 0 equal to 1. This is the first initial condition. Okay. Now our aim is to differentiate this. Okay, the given the integral equation can be differentiated. So differentiating this integral equation 2 with respect to x, we will get this y dash of x is equal to the integral derivative of 1 is 0 plus d by dx of this integral, that is integral 0 to x minus t f of t dt. Okay, plus lambda into d by dx of this integral, which is integral 0 to x t minus x y of t dt. So here we need to use the Leibniz rule that we discussed in the previous lecture. Okay, which is nothing but we have this was our Leibniz rule, that is d by dx of integral a of x to b of x f of x zeta d zeta is equal to integral a to b dou f by dou x d zeta plus f of x comma b of x into b dash x minus f of x comma a of x into a dash x, where a of x is the lower limit and b of x is the upper limit of the integral. Okay, so here the lower limit is 0 and upper limit is x. So since the lower limit is 0, we have this term will be 0. This 0 dash will be 0. So this term will be 0. Okay, so here our f is this x minus t into f of t. This is our capital F now. So first we have to find the derivative dou by dou x of integral 0 to x dou by dou x of this. Okay, that is dou by dou x of x minus t into f of t dt, plus the second term will be f of x comma beta x bx. Here b is nothing but x here. So when we replace t by x, we will have x minus x. X minus x will be here, so this term will be 0. So the second term will be 0, and third term will be 0 because we have the lower condition is 0. So lower point is 0. So 0 dash is 0. So here also 0. Now this integral is nothing but lambda into integral 0 to x, the dou by dou x of this. This is we are taken as capital F. So dou by dou x of this plus here also we have t minus the factor t minus x. So when we replaced t by x, we will get 0, and the third term is here also 0 because the lower limit is 0. Clear? Now this is equal to integral 0 to x dou by dou x of this. Dou by dou x of x minus t into f of t is nothing but f of t itself, because x into f of t, that is the derivative is f of t, and derivative of minus t f of t is 0. So this is integral 0 to x f of t dt. So here also lambda into integral 0 to x dou by dou x of this is nothing but minus y of t dt. Clear? So minus y of t into dt. So we have y dash of x is nothing but integral 0 to x f of t dt minus lambda into integral 0 to x y of t dt. So from this we get the second initial condition, which is y dash of 0. Where at x equals 0, we have y dash of 0 is equal to integral 0 to 0, that is 0 minus lambda into integral 0 to 0, which is 0. So we obtain both the initial conditions. First one is y of 0 equal to 1 and y dash of 0 equal to 1. Now we have to we obtain this in this also integral equation. Here the integral is involved here, so we have to differentiate again. Okay, so differentiating again this equation with respect to x, we will get y double dash of x is equal to d by dx of this integral 0 to x f of t dt minus lambda into integral d by dx of integral 0 to x y of t dt. Okay, here also we will get, by using the Leibniz rule, we will get f of x here, and here is y of x. Okay, directly we will get this, because here first and third term will be 0, because third term will be 0 because here is 0 and here also 0. So the first term will be 0 because here capital F is a function of t only, so dou x of f is 0, and the second term will be replacing t by x, that is f of x into x dash is 1. So the second term will be only non-zero, so here also the second term will be y of x. Okay, so the uh, integral differential equation is nothing but y double dash plus lambda into y equal to f of x, with the initial conditions y of 0 equal to 1 and y dash of 0 equal to 0. So this is the required initial value problem, okay, which is the required initial value problem, clear, corresponding to the given uh, integral equation. So we obtained that an integral equation or an initial value, second order initial value problem can be converted into Volterra integral equation of second kind, and a Volterra integral equation of second kind can be converted into initial value problem. Okay, initial value problem means it contains only the initial conditions, that is at the initial condition is only at the point initial points. Okay, so in the Volterra integral equation, we have the integral as the limit from a to x, where x is the variable and a is the constant. So this is the a is the our initial point. Okay. Now we can illustrate the method of converting a boundary value problem into corresponding integral equation and vice versa. Okay. So here the boundary value problem has the boundary conditions when x equals 0 and x equal to L. So here we have our question is convert the boundary value problem this into corresponding integral equation. Okay. So since it is a boundary value problem, the corresponding integral equation will be Fredholm integral equation. Okay. So here to integrate or to find the Fredholm integral equation, corresponding Fredholm integral equation, here also we have to integrate this differential equation over the interval 0 to x, not the interval 0 to L. Okay, here the points, the boundary points are 0 and L, that is the interval is 0 to L, integrating 0 to x, clear. To convert the initial value problem and the boundary value problem, here we are integrating only over this interval 0 to x or a to x. Okay, here the initial point is a. Okay, so here the boundary points are 0 and L. So 0 to L means here we have to integrate 0 to x. Okay, so that is we'll get integrating y double dash, we'll get y dash. So y dash of x minus y dash of 0 plus lambda into integral 0 to x y of t dt, which is equal to 0. So but here we cannot replace this y dash of 0 as in the case of uh, 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 initial value problem here, because we are not given the initial condition for y dash. Okay, so it is, we know that it is a constant because it is the value of y dash at the point x equal to 0. So it is a constant, we know that. So here we cannot replace this y dash of 0. Now integrating again this equation with over the interval 0 to 0x. So we will get integrating y dash of x, we will get y of x minus y of 0. Okay, minus integral of y dash of 0. Y dash of 0 is a constant, so integral of y dash of 0 is y dash of 0 into t from 0 to x, that is x itself. Because here we have to, if you are integrating this, we will get integral y dash of 0 dt from 0 to x. We will get y dash of 0 is a constant, so integral 0 to x dt, it is nothing but x itself. Okay, so y dash of 0 into x plus lambda into integral 0 to x into integral 0 to x y of t dt equal to 0. So by using replacement lemma, we have this can be written as integral 0 to x minus t into y of t dt. Okay, and we are given the initial the boundary condition. The first boundary condition is y of 0 equal to 0, so we can replace that here. And now this is our differential equation, that is integral equation y of x is equal to uh, x into y dash of 0 minus lambda into integral 0 to x minus t y of t dt. So to obtain the corresponding the integral equation, we have to find the value of y dash of 0. That is, we have to find the value of y dash at x equals 0. So for that, to obtain this y dash of 0, we can use the second boundary condition. The second boundary condition is y of L equals 0. So we can apply that boundary condition also to obtain y dash of 0. After obtaining this y dash of 0, we will get the required initial integral equation. Clear? So this method is only for boundary value problems or converting into Fredholm integral equation. Okay. Otherwise, we were given the conditions y of 0 and y dash of 0. Okay. So here, applying this second boundary condition, which is y of L equals 0, we have this is why when x equal to L, we have y of L here. So 0 minus 0 minus y dash of 0 into L, because when x equal to L, so we have y dash of 0 into L plus lambda into integral 0 to L minus t y of t dt equals 0. That is when x equal to L, when x equal to L. Okay. So here we have to replace this minus y dash of 0. So from this we get minus y dash of 0 is equal to lambda by L into integral 0 to L t minus L into y of t dt. Okay, so we can replace this minus y dash of 0 here. So equation number 3 can be written as y of x plus this x into y minus y dash of 0. So this is lambda x by L into integral 0 to L t minus L y of t dt plus lambda into this plus lambda into integral 0 to x minus t y of t dt, which is equal to 0. So this is our integral equation now, but we have to change this into, here we have 0 to L and here we have 0 to x. So we can split this into 0 to x and x to L. Okay, so here we can write this y of x is equal to lambda by L into integral 0 to L x into L minus t y of t dt plus lambda into integral 0 to x t minus x y of t dt. Okay, so taking this these two terms into right hand side. Okay, so this is equal to lambda into integral. So we are going to split this integral. Here we have our the interval is 0 to L. Okay, interval is 0 to L. So so we are splitting this integral t. So that is t varies from 0 to L. So we are splitting our integral here. This is 0 to x. So we are splitting this 0 to x and x to t. So we can split this integral 0 to L as integral 0 to x plus integral 0 to x to L. Okay. So this is equal to lambda into integral 0 to x by L, taking this L outside inside of this integral. So x by L into this plus lambda into integral x to L. So this integral 0 to L can be written as integral 0 to x plus x to L. Okay, integral x to L. So plus this term is this lambda into integral 0 to x t minus x into y of t dt. Okay. Now we can combine these two terms. Okay, then integral 0 to x terms. So this is nothing but lambda into integral 0 to x. Taking this outside, adding these two integrals, we'll get x minus x by L into L minus t plus t minus x into y of t dt. Taking y of t outside from these two integrals. Okay, plus lambda into integral x to L x by L into L minus t y of t dt. This is the same as. Okay, now this is adding this, we'll get x into L minus x into t plus TL minus XL divided by L. So we can cancel this XL minus XL. So here we'll get lambda into t by L into t can be taken outside, so t by L into L minus x into y of t dt. So this is the first integral, and the second integral from x to L x by L into L minus t y of t dt. Clear? So this is our required for the integral equation was, because we can combine these two integrals like this: y of x equal to lambda into integral 0 to L k of xt y of t dt, where k of xt is this when t less than x, and this k of xt equal to this when t greater than x. Okay, so here we have y of x is equal to lambda into integral 0 to L k of xt y t dt, where the kernel k of xt is equal to t by L into L minus x for t less than x, and kernel which is x by L into L minus t for t greater than x. This interval is actually 0 less than x, t less than x, and this is second interval is x less than t less than L. Okay, so we converted our boundary value problem into this Fredholm equation. This is the required Fredholm integral equation corresponding to the given uh, boundary value problem. Okay, it is of second kind. Clear? Where the kernel k of x is k of x comma t equal to this. So from this we can say that the boundary problem can be converted into the Fredholm integral equation of second kind. Second order boundary value problem can be converted into Fredholm integral equation of second kind. Now conversely, a Fredholm integral equation of the second kind can be converted into a boundary value problem of second order. Okay, so this can be illustrated by using this same example. So we can take this as the Fredholm integral equation of the second kind, and we can show that the corresponding boundary value problem is the given differential equation. Okay. So take this, consider the boundary value of 5. So this can be written as this. Okay, where k of x the kernel is this. So using this kernel, we can write this uh, integral equation as this. So we are going to convert this integral equation into corresponding. So consider this integral equation. So from this itself, we can find the boundary conditions, because when x is equal to 0, we already given that the boundary points are 0 and L. Okay, so when x is equal to 0, we have here 0 to 0, so this integral is 0, and here lambda into integral 0 to L, x is 0 here, so here also to L, we have integral 0 to L. Here is L minus L. So we have this term will be 0. This integral will be 0, and here on the second integral we have L to L. So it's also 0. So the boundary conditions are given from this obtained from the given integral equation itself. Okay. Now we have to differentiate first. So differentiating this integral equation number 4 with respect y dash of x is equal to lambda into d by dx of this. So taking this as f, we can use this dou x of this. So the we have to replace, so x by L into L minus x into y of x. So that will be this into x dash. X dash is 1. Okay, into 1 is here, minus here is 0, so into 0 dash is 0. So this third term is 0. Okay. Now plus lambda into derivative of this. Derivative of this integral is by using this Leibniz rule. We have integral x to L dou by dou x of this. That is dou by dou x of this is nothing but yeah, this is x by L into L minus t y of t dt plus here is the upper uh, point is L, so L dash is 0, so the second term is 0, and the lower point is x, so we have to replace t by x into x dash. So this is x by L into L minus x, replacing t by x, so L minus x into y of x into x dash is 1. So this is the first derivative y dash of x. So we have to differentiate this with respect to x, so that is we will get y of t. So differentiating that term will be 0, and the second term is t by L into minus x into y of t. So is t by L into minus y of t, that is minus t by L into y of t dt. Plus here is the x by L into L minus x into y of x is here, and here also the derivative of this with respect to x is L minus t divided by L into y of t. Okay, and here is also minus x by L into L minus x. So we can divide these two terms, minus x by L into L minus x into y of x. Here also minus x by L into L minus x into y of x. So we can divide or cancel that terms, because yeah, okay, then That means y dash of x is equal to lambda into integral 0 to x minus t by L into y of t dt plus integral x to L minus t divided by L into y of t dt. So this is y dash of t. Now here this is there is integral sign, so we can differentiate again. So differentiating again with respect to x, we will get y double dash of x is equal to lambda into dou by dou x of this. First term will be dou by dou x of this, but this is a function of t only, so this first term will be 0. Okay, then the second term is when replacing t by x, that is minus x by L into y of x into x dash is 1 plus the third term is 0 dash will be 0, that is replacing t by 0, that's also 0, so 0 is here. And here integrating this, the first term is 0 because dou by dou x of this, it is 0 because it is independent of x, plus the second term is we have to replace t by L and into L dash, so L dash is 0, so here we have this 0. And third term is we have to replace t by x into x dash, so L minus x divided by L into y of t into x dash is 1, so negative of that. So this is equal to, this is minus x by L into y of x, this is plus x by L into y of x here, so we can divide this, so this is then the remaining term will be minus L by L, that is minus y of x here, so lambda into y of x, so y double dash is equal to minus lambda into y of x. So this is the required integral differential equation, which is y double dash plus lambda y equal to 0 with the boundary conditions y of 0 equal to y of L equal to 0. Okay, so here we converted the Fredholm integral equation into the corresponding uh, boundary value problem. So here the important thing is that in the boundary value problem, we will be given y of a equal to some a1, y of b equal to some uh, b1. So we will be given the boundary condition. So the corresponding integral equation will be Fredholm integral equation, that is integral a to b. The boundary points will be the integral a to b. And for the initial value problem, we only given y of a equal to some y naught and y dash of a equal to some y naught dash. So we are given only initial points. So the corresponding integral equation will be a to x. So this is the Volta integral equation, and this was Fredholm integral equation. So and vice versa. So we can convert certain equations, certain boundary value problems or differential equations can be converted into integral equations, and integral equation can be converted into differential equations. Okay, thank you.